Hello, and welcome to FPGA Design for Embedded Systems. In this video, you will learn the concept of using a VHDL program called a test bench to test another VHDL program, your code that you've written previously, how to write a simple test bench, how to use loops to generate stimulus, and how to use assertions to determine and report test results. What is a test bench? A test bench is a program written in any language for the purpose of exercising and verifying the functional correctness of the hardware model as coded. This is also known as a test fixture or a test harness. A test bench is a powerful tool for generating test stimulus and test results. A test bench can have several functions, including a top-level test bench declaration, stimulus, response, and component signal declarations. The component, or device under test, this is the instance that you've created earlier. So this is your adder or your CPU or the top-level SoC. A test monitor, which logs the results and reports any miscompares and tells us whether or not the test bench and your code has passed or failed. Here's an example of a test bench structure and how we might exercise your core. The core is the code that you have written, the device under test. This could be any level of hierarchy. And your test bench provides the test stimulus as well as comparing the results. In your core, you might have inputs such as clock in, reset in, data in, 31 down to 0, and outputs, divided clock out, a done output signal, a data B output, 31 down to 0, and a log file. So in your test bench, you could create an output which compares expected values, counts miscompares, and gives you a final pass or fail of your core. Here's an example of an adder test bench. Now note that in our entity, we have no port list. It's empty. Here we have our architecture. We have two data inputs for our adder 4, a bus 3 down to 0, our carry in, carry out, and sum, a bus of 3 down to 0 output. Inside of our architecture, we're going to define some local variables, signals A, B, which will be associated with data, a carry in, our sum, test bench sum, which is an output, carry out, which is an output, and we're going to create a local variable called expect. This will be our compare value for our sum output. Inside of our test bench, we're going to declare our instance, and our instance is our device under test. So here we're going to create a port map to that device under test. Data 1 bits are associated with A test bench bits that we created as a signal. Data 2 are associated with B test bench signals. Carry in, carry out with carry out test bench, and sum with sum out test bench. And in this case, we're just going to create a very simple poor coverage stimulus drawn by hand set of waveforms. So here's our stimulus. We're going to create a process for our stimulus. We're going to wait for 0 nanoseconds and then set an A output of 0, 0, 1, 0. This is the value 2. A B output of 2, a carry in input of 0, and an expected value of 4. At the next time tick, 10 nanoseconds later, we're going to set outputs for A, B, carry in, and our expected value. Another time tick, wait for 10 nanoseconds, set A to 2, B to 4, carry in to 1, and our expected of 7. This will end our process. Another process will create text output. So this output will create an assertion which will print messages to the screen. We've got quite a few messages just to set up our final output, or our final assertion of these messages. So in this case, we want to print to the screen and format that string of space A equals, and then after that string, print to the output our A underscore test bench value. And then we'll place another space, our B output, as a string, and our B variable. And continue on this so that we can create a full line of inputs and outputs and expected values in our string. Our string is an assertion, assert false, report time image now. Time image now is the clock tick that we're currently on. String out all is our string that we've created up above. End process and end architecture. And what happens when we run this code through Model Sim? When we click the Run button, we can see quite a few messages on the screen. Here I've cleaned up some of those messages. So now we can see our first clock tick 0 nanoseconds. We see our inputs, A is 2, B is 2, carry in is 0, and sum in the first clock tick is X unknown, and carry out is X unknown, and our expected value of 4. At the next clock tick of 0 nanoseconds inside of the simulator, and this is normal, in the next clock tick of 0 nanoseconds, we have sum showing 4 and our carry out showing 0. So the clock tick has been updated. At our next clock tick of 10 nanoseconds, we have A of F, or 15, B of 0, carry in of 1, and our sum result output is all zeros, and our carry out in our text message has kicked over to the 1 value. So we've rolled over our 1111 and added a carry out. And our expected and our sum are equal. At the next time tick, 20 nanoseconds, we have 2 plus 4 plus a carry in of 1 gives us a sum resulting value of 7. And that matches exactly with our expected value of 7. And here's what our waves look like. In A, 2, F, and 2. In B, 2, 0, and 4. And then our sums of 4, 0, and 7. And you can see our carry out bit going high. Next, we'll show some automation by creating loops. Rather than hand generating a set of waves, here we'll create each time tick, wait for 10 nanoseconds, we'll create a large loop. I, 0 to 15, J, 0 to 15, K, 0 to 1, and create a large loop so that we cover all possible expected stimulus values and provide our expected value of A plus B plus carry in and compare each time. So now we've got more coverage by creating an automated loop. And here's what the waves look like. We've got our A's toggling, B's toggling, and carry in toggling with our expected compare values going to the output. And here's an example of a self-checking statement. So we've got our expected value of A plus B plus carry in. And if, so now we're going to compare, if our sum does not equal A plus B plus carry in, then write a message to the screen, error in the sum, and write that string output to the screen. In this video, you have learned how to create loops to generate stimulus. You've also learned how to use assertions to report test results and automate your design coverage.